Okay, so we have Dr. Chandra, whom all of you are already familiar with, and he has agreed to give us a couple of lectures to cover some actual implementations of qubits, and he will also then in particular focus on the gates that are available on the IBM processor. And as many of you may know already, the IBM quantum processors, some of them are accessible on the cloud, and he will show us a few things about how to implement basic gates, how to run a circuit. And the hope is that you pick this up, and then we'll actually have you do an assignment. One of the assignments will actually be on implementing certain circuits on IBM Q processors. Okay, and this is what I was just discussing with Chandra. All of you simply need to go to the IBM Q page, use your Gmail accounts and log in. It's as simple as that. If you haven't done that already, I encourage you to please do that, because now we have all the tools that we need. You can actually go and start running simple circuits already on your own, right? And with that, I hand over the floor to Chandra. So go ahead, Chandra.
Okay, Prabha. Thank you very much, and thank you for asking me to give these lectures. So as Prabha was saying, now we have moved on from the theoretical part of quantum information to something which, something like a practical part of quantum information, something we can play around with in terms of devices and test whatever we have learned. So IBM Q is one of the places where we can test our ideas or like our learning of quantum information. So IBM Q is a quantum computer made by IBM, and you can access it through the cloud. Okay, so the basic thing is you have a website for IBM Q. You need to create a login, as Prabha said. You can use your Gmail account to create the login. Then once you log in, there are certain machines which are freely available for everyone. And I think currently we have a maximum of 7 qubits. The biggest one we can get through is 7 qubits. And with this 7 qubits, you can actually verify some very nice and simple quantum protocols like teleportation, quantum secret sharing, and super dense coding, and so on. Like there are other things like time, or what is that, bit flip errors, phase flip errors, and all those things. So before I start teaching this IBM quantum computer, how to use IBM quantum computer, I would like to give a basic overview about the different qubits available. What I mean by different qubits is, it's not about IBM. Like what are the different kinds of qubits? Like there are physical systems, and these physical systems can be made into qubits. What are the different physical systems which can be made into a qubit? And what are the conditions under which we can make a quantum computer out of these qubits? Okay, this will be the main focus of today's lecture. So before I go into qubits, I'd like to say that the basic in classical information theory is a bit. Okay, bit. And in a bit, what you do is you have only two possibilities, 0 and 1. You use just these two possibilities to encode any possible information in the information, or do any possible computation or anything like that. Okay, so if you look at the origin of this bit, it came from the time when we first started using telegraph. Odd, but the origin of bit is actually like around the 1840s or something. In telegraph, we had two things, a short pulse and a long pulse. This was something like dot, and this was called a dash. The entire alphabet, special symbols, and everything were actually encoded through these two components. Okay, so this actually we can say this created the whole idea that whatever information you have can be encoded with only two possibilities. The reason why you try to use only two possibilities is you can associate these two possibilities, let's say 0 as something with a lack of voltage and 1 as something with having a voltage. If you discretize it, it's actually easier to work in electrical circuits, because if you have something like a let's say a voltage of 5 and a voltage of 7 for a 0 and a 1, then sometimes you will have something between 5 and 7. So what happens to that? So it's actually a question which is not easy to handle technologically. So what they prefer to do is use bits. Now, when you come to quantum information theory, we have something called a qubit. So in a qubit, there are two possibilities as in a bit, a 0 state and a 1 state, but your quantum state can always be in a superposition of the two states, such you have the mod a plus square equal to 1. This superposition, where you can combine the 0 and the 1, actually gives you a lot of possibilities to work with. And this is actually the power behind quantum information and quantum computation. Okay, so now when we start talking about qubit, we need to see how to qubit, how to create bit out of a physical system. So here, what I mean by a physical system is something like an electrical circuit or something like a light wave, something like this. Can I create a qubit using any one of these things? So it's actually, there are many possible ways in which you can do that. I will give some of the most popular ones which are available. So yeah, before we actually look at the qubits, I should tell you something more. A qubit, as you know, as I said, has only two levels. One of the most natural qubit we have is the atom. If you take an atomic system and let's say, if you look at the levels of the atomic system, the way it looks like is, let's say this is the potential of the atomic system. So you have the ground state here, then you have the first excited state here, then the second excited state here, third here. So let's call this as 0, 1, 2, and 3. Here you would see that the energy gap between the 0 and the first level is actually higher than the energy gap between 1 and 2. So you can always isolate these two levels in the atom and use it as a qubit. So now you contrast this with a quantum harmonic oscillator. So if you look at a quantum harmonic oscillator, this is the potential of a quantum harmonic oscillator. You will always have equally spaced levels. Okay, so what happens when you have equally spaced levels is the energy gap is between 0 and 1 is same as the one between 1 and 2. So you cannot isolate two levels and use it as a qubit. The involvement from the other levels is always present. So if you use a light wave to drive an atom from the ground state to the excited state, you can do it you will have to find the energy gap here. Let's call this energy gap as delta E, and you can find the frequency of the light needed. Using this, you can drive this thing. But if you do the same thing here, you will not be sure if you are driving it from the 0 to 1 level or 1 to 2 level, or you can drive it between any two arbitrary levels and you will not be sure. So you cannot isolate any two levels. So atoms are the most natural forms, okay, form of qubit. So you can use atom as a qubit, but there is a problem with this. Sometimes you need to address each atom individually. Okay, individually addressing them. This because atoms are very small and you cannot pick up them and try to manipulate it as easily as you'd like to do it. Okay, so to overcome this, what we have to do is we have to look at macroscopic systems or systems a little bigger than atom. What I mean by macroscopic is little bigger than atoms. Okay, and you will have to try to create atomic kind of a spectrum in that. Like you should have some kind of unharmonicity between the levels such that you will be able to isolate two levels and use it as a qubit. These kind of macroscopic systems called as artificial atoms. Okay, so we can use artificial atoms for creating qubits. So one of the first forms of qubit which came during the early times of quantum information theory is the NMR qubit. Here, NMR stands for nuclear magnetic resonance. Okay, so here in NMR, again, there are two types. One is the liquid NMR and the other one is the solid state NMR. Liquid state, solid state. The first one used as a qubit was the liquid state NMR. So the way it works is some atomic nuclei behaves like a spin-off system. Okay, so when you take a liquid and subject it to some kind of nuclear magnetic resonance, it behaves like a spin-half system. But once you take a liquid and do NMR, you are not using one single qubit. You're using many qubits within the liquid. Okay. The thing is, we are not using, or let's say we are not using or addressing one single qubit. What is something of the order of 10 power plus 15 qubits. Sorry, it's 10 power plus 15. You have so many atoms, or like so many atomic nuclei there. Okay, so the interatomic bonds between these two, to any interatomic bonds in a molecule, like here you have some kind of a molecule, NMR molecule, which is usually these are complex. These are complex molecules. So let's say you have this as a qubit. The interatomic bonds can be considered as spin-spin. I mean, these spin-spin interactions, and we can use them to perform gate operations. So here, since we are not using one single qubit, our entire quantum information follows a method called ensemble quantum process. So I hope you guys are ensemble, which occurs in statistical mechanics. Ensemble means you have a collection of identical systems or similar systems. Okay. So what happens here is you do the whole quantum information or quantum processing tasks on a collection of atomic nuclei, not one single nuclei. So you're not doing single qubit quantum computation, you're doing ensemble quantum computation. The disadvantage with the ensemble quantum computation is if you want to scale the number of qubits. Scale means, let's say you are doing a problem with 2 qubits, and now the sample is sufficient for that. But next you want to increase the number of qubits to 4. So you need 2 qubits inside your system. When you want to do that, the amount of sample you need to increase for NMR is very high. So it doesn't scale so easily in a liquid NMR. So this is one disadvantage of liquid NMR. The other advantage is keep increasing this number of qubits or some things. What happens is you have the quantum state goes into a mixed state. Mixed state means you always have your quantum computation happening in the pure state, but when you increase the sample, it goes much closer to the maximally mixed state or the mixed state, and the mixedness is very high. So it's the amount of quantum property present is very less, and you cannot use it for viable quantum computation. Okay. The next one is solid state NMR. And this solid state NMR uses a nitrogen vacancy. Okay. So you have a diamond. Diamond is mostly made of carbon atoms, but sometimes nitrogen atom gets formed as some kind of an impurity in the diamond lattice. Once you have a nitrogen atom, you also have a vacancy next to the nitrogen atom. This nitrogen and the vacancy can be manipulated using nuclear magnetic resonance to give a solid for doing quantum computation. This is solid state NMR. Okay, so these are the two forms of NMR qubits. So if you look at the solid state NMR, here you are working with the nitrogen vacancy, and this is one specific qubit. Okay, so this means you are addressing each qubit individually. Each qubit, like let's say this is one qubit, you are addressing it individually. So you are not using ensemble quantum information or ensemble quantum processing. Not used. So these days, NMR quantum computation is being done, but the number of people doing NMR quantum computation is actually very less. People have moved on from NMR quantum computation to others. So first there was a liquid NMR, then came solid NMR. From the solid NMR, using the same diamond thing, there is a different kind of a qubit called NV's. Hello.
Sir, can I ask you a question?
Yeah. Hello.
Hello.
Yeah, please. Yes, yes.
Sir, you are saying that in liquid state NMR we are having many qubits, and they are having link between each of the qubits. So this link, I mean, I don't. This link is natural.
Okay. So I think I will have to make this a little more clear to you. In a liquid NMR, you take a this liquid state. Yeah, you have a liquid of a liquid of some organic molecule. Okay. The organic molecule, each molecule is like a qubit. but the interactions are within the molecule. Like what I'm saying is, if you have a complex fluid, liquid like chloroform or something like that, the qubit-qubit interactions are within each molecule. Okay, so no two molecules are like two qubits which are influencing each other. Okay. Hello.
Yes, sir. Yes, sir.
Did you understand this? What I said?
That means those two qubits are not affecting each other. That's what you are saying?
Yes, yes, exactly. This comes from this idea of ensemble in statistical mechanics. If you look at an ensemble,
Chandra, can I
it's
just
a collection of particles.
hello?
Yeah.
Hey Chandra, if I can just
Yes,
briefly
Prabha.
step in. Yeah. So
Yeah.
I think there are two different things happening here. One is a liquid sample. So this kind of molecule, sample molecule that Chandra has drawn, a typical liquid sample will have like Avogadro number of these molecules, right? Or, something like 10 to the 15 of these molecules. So if you want to talk about just a single qubit system, then this liquid sample you can identify one of these nuclear spins as your qubit and try to address that because they all have distinct spectral features, right? So then your sample has 10 to the 15 single qubits. So it's an ensemble of 10 to the 15 qubits. If you want to now have two qubit interactions and do two qubit operations, you have to identify two spins in the same molecule because they can talk to each other. But across these different molecules of the ensemble, there is no conversation, there's no correlation. That is like your mixed state, your density matrix that we're all familiar with, right? That is why we say there is nothing coherent when you have this mixture. The coherence is between those two qubits of the same molecule, the two spins of the same molecule. So now if you want to imagine a system where I have 7 qubits or 10 qubits or 100 qubits, it's as if I must have now a molecule which has that kind of connectivity and so on. Right? So I think the maximum people have done is like a 7 qubit register, right, Chandra, or a 9 qubit register on
Seven.
So you have to pick molecules. So there's Professor Mahesh in IIT Pune, for example, who works on, so he picks molecules which have what is called a star topology. So there is one nuclear spin in the center. It is surrounded by a set of nuclear spins. And I believe they find molecules like this where they can go up to 10, so all of them are connected to the one in the middle. And that is how you then connect them together or something like that. So I hope you understand the difference, Nilesh, between addressing nuclear spins in the same molecule that forms like a single qubit or 2 qubit or 3 qubit system. But there are 10 to the 15 copies of this in your sample.
Yeah. So that's exactly why this is called an ensemble. If you look at the word ensemble in statistical mechanics, what you mean is these are identical copies and these copies do not interact with each other. What you do will change the properties in each one of the copies individually, and you have an averaged out measurement from them. Okay.
Yeah.
Right, Prabha? Yeah.
Thank you.
Yeah, I hope that's clear, Nilesh. Yeah, and I think Sumit has asked whether we're considering the molecules as qubits or the nuclear spin. I think we answered that also, right? It's the nuclear spin. It's a
nuclear spin is the qubit. Yeah. Yeah. Here again, I'd like to say why we are not considering the electron spin, like it has a higher sort of like a decoherence time. I think I will come to those things when I explain the qubit fundamentals in a couple of minutes. Okay. The next one is the NV center qubits. So when we started with this solid state NMR, I told you like one of the candidates is this NV center, using a diamond thing for NV center qubit. So what we have is in a NV center qubit, we have something like this. Let's assume this is the structure of a diamond. Sometimes because of some defects in the formation, instead of the carbon atoms, all these circles are carbon atoms. A nitrogen atom gets introduced, and it sits in between the carbon atoms. Carbon atom has 12 electrons, and it shares them with this thing, with the other carbon atoms in the thing. But when you have a nitrogen atom with 14 electrons coming inside, and there is a vacancy also formed next to it, you will have one free electron or one unpaired electron in this thing, which can be used as a qubit. Usually, using this thing, you can locate a diamond crystal and look for the defects in the crystal. These are called crystal defects, point defects in the crystal. You can look for the defects, and you can use these defects as qubits, and you can manipulate these NV centers using magnetic or electric field, or sometimes using microwave radiation also. Okay, so the problem with these kind of qubits is you will have to find a diamond which has as many number of defects as you want, which is which is not so easy. But nowadays they are coming up with techniques to manufacture artificial diamonds, where during the process of manufacturing they can randomly introduce, sorry, not randomly, they can introduce some defects in the process of manufacturing and create some kind of qubit array or something like that in the crystal. Okay, so this is the NV center. Now, NV centers are very popular, but the problem with NV centers is right now having more than, I think, 7 qubits is nine qubits is the limit up to which they have worked with it. Creating these qubits or these defects in one single diamond lattice is actually a tough thing, and people are trying to increase the number of qubits. So this is where we'll have to look for other kinds of qubits which are easy to create. One of the qubits is the photonic qubits. So you guys are all, I think, familiar with the polarization property of. Okay, so a photon is an electromagnetic wave, which means it has both electrical and magnetic field, which goes like, okay, electrical field in one direction and magnetic field in a direction perpendicular to it. And these fields oscillate in many directions in a general electromagnetic wave. And if we can restrict these to one particular direction, then we can say that the light wave is polarized. Okay, so you can do that by creating some kind of a slit or something like a slit like this, which will a very narrow slit, not a very narrow slit or a filter, which will allow only certain frequencies or only certain oscillations to pass through. So the photonic qubits have different kinds of polarization. One of the is linear polarization. Here, linear polarization means the light wave is polarized either in the horizontal or vertical direction. So you can use the, sorry, this is the vertical, right? Yeah. So you can use these two levels as two forms of qubit. You can call one of them as 0 and the other one as 1. Okay. And the other possible thing is you can use a diagonal or anti-diagonal. That is, when this is the axis, you can use the diagonal or anti-diagonal part of this. I think it should be this way. Anti-diagonal part of the polarization. So that is another set of polarization. Then you have the circular polarized light. So what we mean by circularly polarized light is when we have a polarized. So for polarized light, I said that the waves will be, the oscillations will be present in only one direction. In a circularly polarized light, it will be present in only one direction, but that direction keeps changing with every step of the movement of the photon. Every, like it keeps, I mean, moving. The direction keeps changing from, or is, let's say it is vertical, and then the angle keeps decreasing slowly, and then it keeps it goes to the opposite direction, and then it makes a complete circular precision. So it can circle in the what do you say, like in this direction or this direction. So this is, one is called the left circularly polarized and the other is the right circularly polarized. So this is the right circularly polarized and this is the left circularly polarized. Again, these two things can be assigned as 0 and 1 of a qubit. So apart from this, you can also use the angular momentum of qubits or the path entanglement. Path entanglement is when you generate the qubits, you can actually superpose the two paths of a qubit, possible paths of a qubit, and create some kind of an entanglement. Okay, so you can use all these things as qubits. So a photonic qubit has a big advantage that you can always generate them easily using lasers. So we can generate them using visible laser, microwave, and then we have the IR. Okay, so to work with photonic qubits, we just need some optical elements. Apart from the lasers, we need what are called the half wave plates, plus wave plates, mirrors, and possibly waveguide using the microwave. So if you have a photonic qubit, it can not only do the quantum computation task, it can also move from one place to other and carry the quantum information from one place, from point A to point B. So these kind of qubits can be used in quantum information, and also these qubits are easily scalable. Okay. So apart from these are the regular one. These are the first ones which came. The current one which is being used mostly is this superconducting qubit. So when we say something is a superconducting qubit, what we actually mean is we are using qubits made of so a Josephson junction is nothing but a superconducting element like this, and this is connected to a insulator or a let's say insulator or a conductor, and then there is another superconducting element. So what you have is one superconducting element and another superconducting element, and then there is a insulator in between. So what happens is when you have a Cooper pair, superconducting elements have Cooper pairs, and these Cooper pairs have to tunnel through this insulating thing into the next superconductor. So this causes some kind of phase difference, and these tunneling properties can actually be used to produce some kind of a qubit. So the Josephson junction has two energies. One is the or not the Josephson junction, like that's it. The energy required for the Cooper pair to tunnel is called the Josephson energy EJ, and based on this, there are three possible superconducting qubits. One is the phase qubit. You put up a superconducting qubit. You just put up a superconducting qubit. Let's say this is the symbol for a superconducting qubit, and connect it to some current flow. And once you do that, you will have a potential which looks like this. And each potential has some energy levels. You can choose one of the potential and use these energy levels to use it as a qubit. This kind of a potential is called a checkerboard, sorry, not checkerboard, washboard potential. The next one is you can actually use some kind of an inductor. So you have a electrical circuit with the inductor, which is actually connected to a superconducting qubit here. Once you have an inductor, this is called a flux qubit because you use a flux to drive the Josephson junction, to drive the Cooper pass through the Josephson junction. So this flux qubit has a potential, well potential, and generally these double well potentials have levels which you can use as qubits. But the most popular ones in these things are the charge qubit. The charge qubit, a voltage is connected to a capacitor, and the capacitor drives the electrons across the Josephson junction. Okay, so let me say this is the phase qubit. This is the flux qubit, and this is the what do you call as the charge qubit. So a charge qubit looks like a harmonic potential, harmonic oscillator thing, but it has anharmonic levels like this. Okay, so the charge qubits are the most commonly used ones. So when you look at the energy levels of a charge qubit, generally it looks like this is the energy, this is the gate voltage. The gate voltage is the voltage needed to drive the electrons across the charge. Okay, so you can see these levels are not flat, and you can use the charge qubit only at some special values like this. And these values are called the sweet spots. Overcome this, what is suggested was, okay, this ratio EJ by EC is very important for superconducting qubits, and this ratio tells you how much of energy difference you need between the Josephson and junction and the capacitor to drive electrons. And if this is of the order of 1, you have a charge qubit. If you take this to the order of something like 50, so what happens is, instead of being so wavy, actually the energy levels flatten out like this. Like this. So this is what is called as a transmon qubit. So a transmon is a special kind of a charge qubit, and IBM and IBM, Google, both of them use transmon. Yes, Rigetti also uses, not sure, but IBM and Google both use transmon qubits. Okay, so apart from this, the other kinds of qubits are the ion trap qubits, but penning traps. Penning traps are like electrical and magnetic fields which can capture atom ions of ions and localize them in some region. So these are ion traps. You can use a combination of electrical and magnetic fields to capture charged particles and use it. So there is a company called IIT Q, which has successfully produced a quantum computer using ion trapped ions. Okay, so then we have other atoms. Atoms are just natural atoms, but here the number of natural atoms is of the order of 100. Okay, and then we have BEC qubits. BEC qubits, what we do is mix two different species of atoms and make a BEC. So these two atoms have two different energy scales, and we can use that as two levels of a qubit. So this BEC qubits. So these are the different qubits available to us. But once we want to use them as a qubit, we need to look at some properties they should have. One is one of the important property of a qubit is the qubit frequency. So qubit frequency means you have a qubit. This is the qubit, and this is the first. Okay, there is an energy gap between these. So you can write this energy gap in terms of as actually is as h nu, and this frequency nu is the qubit frequency. So this is an important property of a qubit. Then there is a relaxation time. So once you shift the qubit from the ground state to the excited state, the qubit is not going to stay in the excited state for long. It will come back to the ground state. Okay, so the amount of time it can stay in the excited state, that is given by the relaxation time. Like it tells you the time taken for a qubit to decay from the excited state to the ground state. So this is the relaxation time. Usually this is denoted by T1. The third one is the coherence time. Coherence time is how long can a qubit retain its quantum nature. So when you prepare any kind of a quantum system, it's going to be in contact with an external environment. So this is naturally going to drive the qubit to a classical side. So excuse me. It can drive the qubit. Okay, the qubit can go from being quantum to classical. This time required for a qubit to fall from quantum and become classical is called the coherence time. Coherence time T2. Yeah, it's the coherence time T2. Okay. So to choose the qubits, there is a criterion, a very famous criterion given by a physicist by name DiVincenzo. He gave some basic characteristics with which we can choose the qubit for quantum. I mean, like if we make a qubit out of an arbitrary physical system, we will have to see if these criterion are met. If these criterion are met, then we can use it for making quantum computers or use it in quantum communication. Okay. So, Prabha, can I take 5 more minutes actually? Hello? Hello? Prabha, can I take 5 more minutes?
Yeah, sure. I think there's an issue with my microphone. You can hear me now, right?
Yes, now I can hear you.
Yeah, go ahead.
Okay, I'll just finish the DiVincenzo criterion.
Yeah, few more minutes is fine.
Okay, so if you look at the suitability of using a physical system for a qubit, generally DiVincenzo criterion is like a standard thing to check. First thing, what he says is it should have scalability. That is, now you use 2-qubit system, okay, to construct a Bell state. Then you want to construct a gate, you want to use 3 qubits or more. So you should be able to incorporate new qubits into your system and use them without any problem. That is scalability. Okay. Second is ability to initialize. So you have a qubit state, it's a gate or a excited state. So let's say you have a 5-qubit system and you want to have this kind of a state. You should be able to address each qubit individually and tell qubit 2 you should be in state 1, and qubit 5 you should also be in state 1, and set up this kind of a state. This is the ability to initialize. You should be able to address each qubit individually, and you should be able to create an initial state you require. The third one is long decoherence time. So, because when you have a qubit, it should remain a qubit, or it should remain quantum with qubit nature, as long as you want to do a particular quantum task. So for this, you should have longer decoherence time for the qubits. Okay. Then the next one is you should be able to implement a universe of quantum gates. So you have seen what quantum gates. So you should be able to implement a universal set of quantum gates using your qubits. Okay. Final measurement capability. So you should be able to each qubit individually, get information out of them. Okay. This is the measurement capability. Apart from these 5 properties, there are separate properties for quantum communication. That is, okay, before we go to this, I'll say this. So in all the qubits we saw, except for the photonic qubits, most of them are kept in one place and used there. But the photonic qubits have the special property that they go from one place to another. We can classify the qubits into stationary qubits and flying qubits. All the qubits like NMR qubit or the superconducting elements and all those things, Josephson junction qubits, are all stationary qubits. Photonic qubits are flying qubits, in that they can take the quantum information and move from one stationary qubit to another. Okay, so when you use 2 superconducting qubits, you'll always have microwave waveguides between them, because you need to transmit information from one superconducting qubit to other using microwave photons. Okay, so in quantum communication, we should be able to transfer information from a stationary qubit to a microwave qubit, or stationary to flying qubit and back. So which means if you have a superconducting qubit here, you send out some photons, and there should be another superconducting qubit which receives it and processes it. Then it sends out back information in terms of a different photon, which the first qubit can actually receive. Okay. So the second property is it should be able to transmit flying qubits to any specified location without any problems. Like there should not be any problem with transmitting these flying qubits from one place to another. Okay, so 7 properties are called the DiVincenzo criterion. The first 5 are useful for quantum computation, and the last 2 are useful for quantum communication as well. Okay, so I think we have looked at the realization of qubits and the criterion needed for a qubit to be useful in quantum computation and quantum communication processes. Tomorrow, we will look at how to create, how to create an account on IBM Q, and how to use it for constructing some quantum states. Okay. So, do you guys have any questions here?
Sir, this, in the definition of this coherence time, we are saying that time required to move from quantum to classical nature. So does that mean to from superposition state to the collapsed state?
In a sense, yes. So what happens is quantum systems do not remain quantum forever. That's one of the harsh realities we have to live with, and it will actually collapse to something classical, and this collapse is highly time dependent. Like for different qubits, there's a different decoherence time. For example, NV centers, I think it is of the order of microseconds, I guess. But if you go to superconducting qubits, since they are electrical circuit and you can actually make the circuits according to your necessity, there are things that worked up to like a couple of milliseconds, or like possibly even 50 milliseconds. You can retain it as quantum up to even 50 milliseconds in superconducting qubits.
That means before.
Hello?
So that means before measurement, if we are not going to measure the qubit for a sufficient amount of time, then it will itself collapse to the ground energy scale. That's what.
Yes. That is because of the environmental effects.
Yeah.
It has nothing to do with the thing. These are open systems. Open system means there is always an environment, and the environment actually interacts with these qubits. And the environment supplies some energy, takes some energy, something like that. And this will collapse the quantum state.
Yes.
Okay. So Avik, your question is, the photonic qubit is an example of flying qubit. Yes, it is an example of flying qubit, and it is used with all the qubits like NMR, NV centers. Even NMR uses some kind of an electric field, and superconducting qubits and all for transfer of information. If you look at quantum communication, one of the important aspects is transfer of information. And transfer of information can be done through two ways. One is using what is called as a quantum wire. A quantum wire is nothing but a linear array of spins in which you give the information at one end and change it, and then this information passes from one spin to other and reaches the other end. Okay, the other way is using a flying qubit. Okay. Thing is, if you want to do it over short distances, quantum wires can work as well as flying qubit. But if you want to go for long distances, these wires have their own inherent losses and so on, which makes them not suitable. So if we can use a flying qubit, we can just send the information from one place to other. So in this recent quantum communication by satellite experiments, they have used photonic qubits to send quantum information from ground state to a satellite in low Earth orbit. Okay, so that's like hundreds of kilometers. Okay, so if we take a system which has spin 1 system, will it be considered a qubit or Q-trit? It's a Q-trit. If there are 3 distinct spin levels, as Professor Prabha says, it will be a Q-trit. Okay, any more questions?
Okay. So yeah, let's thank Chandra, and we'll see you all tomorrow with some live demos on some information on the actual IBM Q processors and some simple demonstrations.
Okay. Thank you, Prabha.
Yeah, thanks, Chandra. Very nice.